Okay, so now let's move on to the next topic, which is on enols and enolates. So in this lecture, what we'll do is we'll do a little bit of recap of some of the concepts that we learned previously, and introduce you to some new concepts of enols and enolates. Okay, so to begin with, let's start with an experiment. So the experiment that we want to conduct is an NMR experiment. So as many of you already have some exposure to NMR, in that you may not know all the details about the instrumentation and so on, but what you know is that it's a reflection of the number of distinct protons that you would expect to see. Okay, so therefore, if in a molecule you have three different kinds of protons, then you should see three signals. So with that information, we should be able to look at this NMR spectrum and understand it. Okay, so what I've done here is I've just this is a theoretical NMR spectrum that I have obtained from ChemDraw, and so here what you expect to see is that you expect to see there are three kinds of protons. Okay, so let me just draw out the structure for you in its full structural formula so that you understand this. Okay, so there is a cyclohexane ring, and then this is a ketone. Okay, and let's start with this hydrogen. So this is a CH3. So this I'm labeling it as A, and this CH3 is identical to this because you have a plane of symmetry in the molecule. So therefore A would be one kind of signal that you would expect. The next proton that we are interested in is the CH2, and not only the CH2s equivalent to each other, but they're also equivalent to these two CH2s over here, and therefore I have labeled it as B. Okay, and so you can take some time and draw out the structure and make sure that what I'm saying is correct, but you have two planes of symmetry in this molecule, and so therefore you can imagine that they would be similar. And the last signal, last distinct set of protons is this over here, which is basically a two proton signal, which would correspond to the two hydrogens alpha to the carbonyl, which I'm labeling it as C. Okay, so therefore, although this molecule has many hydrogens, so it has 6 plus 4 plus 2 are 12 hydrogens, you will still see only three signals in the molecule, one corresponding to 6 hydrogens, which is for A, and one corresponding to 4 hydrogens, which is for B, and one corresponding to 2 hydrogens, which is a C. Okay, so this is the NMR spectrum that I would expect from this molecule. And this molecule, by the way, is called as dimidone, D-I-M-E-D-O-N-E, dimidone. It's a very interesting molecule. It's quite widely used for various synthetic and as well as analytical applications. So this is the spectrum that I would see. Okay, but now when I actually go and record the proton NMR spectrum, what I see is that I do see these three peaks, that is A, B, and C, as I have listed here, but we also see some additional peaks. Okay, so these additional peaks here are labeled in black. So here are the additional peaks, which I'm now highlighting. There's an extra peak here, there's an extra peak here, here, and here. Okay, and so just to be clear, the sample is actually clean. The compound is pure. It has only dimidone in it. So this is not reflection of an impurity. Okay, so therefore the majority of the compound is still dimidone, and this is recorded in deuterated chloroform, but it seems like there is an additional peak that is being produced. Okay, so in order to understand this, let me just draw out one possibility, is that if you have dimidone, which is whose structure is as shown here, C double bond O, C double bond O, methyl, methyl. Now it is possible that since this is a keto form, it is possible that you could have what is known as enolization that can occur. So this is a phenomenon that you guys have already studied in maybe 12th standard or so, but this is a possibility. So if it forms an enol, so the structure of the compound will look something like this. So you have C double bond O, OH, and this hydrogen. Now, what is apparent from the NMR spectrum is that if it's an equilibrium between these two structures as shown here, then the methyl groups, which are over here, are actually quite far away from the enol, and therefore you would see only a small shift in the NMR spectrum. So if I go back to the NMR spectrum and look at it, you see that this black peak that is being formed is actually quite close to A, and so you could expect that it's going to be the 6 methyl groups. Okay. Now coming to B, so that is the A, and now coming to B, what we would see is that B is substantially closer to the enol, and whatever changes that occur in the structure are going to be reflected more closely. And so you do see that the B protons are actually quite distinct from the A. And there are further aspects to this NMR spectrum which I will not discuss at this point, but you will actually see that these 2 protons which are next to it are going to be different from the other 2, and so on. But one more piece of important evidence is the production of this new hydrogen, which from our past experience of olefins, so if I just take a regular olefin, this shows somewhere between 4.5 and 6, depending on what are the other functional groups that are present. And indeed, when we look at the spectrum of dimidone, we see a peak here at 5.5. So together, what this suggests is that there is a significant amount, a small but significant amount of the enol that is being produced. Okay, so this phenomenon is known as tautomerism. All right, and this is again something that you have studied previously. I'm just recapping. So in this tautomerism, what happens is that if I draw an arrow pushing mechanism, then it's going to look like this. So I have C double bond O, C double bond O, and the important protons here, I'm going to just draw them out so that it's easy for us to understand these 2 CH. And what is actually happening is that this carbon hydrogen bond breaks, and it goes now, and these electrons form a bond between carbon and carbon, and this goes and picks up a proton. Okay, so if this happens, then you get a structure such as this, where you have the main skeleton of the molecule remains the same, the C double bond also remains the same, but you have a new carbon-carbon bond between these 2 carbons, and then you have an OH that is formed, which is the enol form. Okay, and now of course this enol can again pick up, move an H plus and form the ketone back. And so the important aspects here are, this is called the keto form and this is called the enol form. Okay, so what you need to know is that this is a phenomenon where there is only a transfer of H plus. Okay, so transfer of H plus, and there is no change in the pH. Okay, so it picks up a proton, and if you see here in this process, it actually gives up a proton. So therefore there is no change in pH of the medium. So if I start with neutral compound, I'm just going to get a neutral compound back. Okay, so this is, again, we want to draw an analogy with the carboxylic acid. So in a carboxylic acid, you actually, we are very familiar with writing these structures, and let's imagine that these 2 oxygens are different. Then you could think about the same process, which is reacting with an H plus and forming this, and it's going to be in equilibrium with the other tautomer. Okay, although normally we don't think about this manner, but indeed the conversion of one carboxylic acid to the other form is actually a tautomerism process. Okay, but the reality is that if we now move on to regular aldehydes and ketones, so I have myself recorded NMR spectra of many aldehydes and ketones, and so have many of my colleagues in my lab, and invariably we almost never ever see a peak for the enol. So if I take a regular ketone such as acetone and record the NMR spectrum, although I just told you that it is possible that it will form the enol, but when we record the NMR spectrum, we almost never see the enol form being prevalent. Okay, and so one of the reasons for this is that, if you look at the stability of these species, I'm just going to draw some bond strengths over here. And so let's bear with me, this is the keto form and this is the enol form. So the bond that we're looking at is between X and H. And for the keto form, this is 440, whereas for the enol form, it is 500. So this is the bond strength of the carbon hydrogen bond as shown here, and this is between oxygen and hydrogen. Okay, now if I look at the pi bond strength of the C double bond O versus the C double bond C, and so for the keto form it is 720 kilojoules per mole, whereas for the enol form it is 620 kilojoules per mole. Okay, so now what we can do is, if we can consider the sum of these two, so that we can compare how much of energy we are losing or gaining in the process. So if I sum these two values, then I should get the overall bond strengths. So in this case, in the case of the keto form, this would be the pi bond strength, and for the keto form it is C double bond O, and for the enol form it is C double bond C, and this is something that we have already studied. And now if I add these two values, here I get 1160 kilojoules per mole, whereas here I get 1120 kilojoules per mole. Okay, so therefore the enol is slightly less stable by about 40 kilojoules per mole compared to the keto form. So the equilibrium constant that we usually find here is in the range of 10 power minus 6. Okay, so let me just rewrite that so that it's easy for you to follow, and maybe I should write it here on top of the arrow. So the equilibrium constant is in the range of 10 power minus 6. Okay, so what does this equilibrium constant of 10 power minus 6 mean? So if I have to take two components, A and B, A in equilibrium with B, if the equilibrium constant is 10 power minus 6, that means that the percentage of B that is going to be produced would be, basically it's 1 part in 10 power 5, which would be a 0.01%. Okay, so it's a really small number. And in terms of NMR spectra, we usually observe impurities or components of a mixture which are in excess of 1 to 2%. So sometimes you don't see components which are less than 1%. Many times you don't see this. So therefore, clearly by NMR, you will not be able to detect the enol. Okay, but the enol is actually reduced, and there is experimental evidence for this, and I'm going to share with you this experiment that has been done. So the experiment that has been done is fairly straightforward. So what we do is we take this compound, this ketone PH C double bond O CH2CH3, and dissolve this in D2O. Okay, and what we know is that D2O, much like H2O, is going to be in equilibrium with D plus and OD minus. Okay, and so this, much like water, the amount of the D plus and OD minus is going to be so low, but yet it is present in solution. And so therefore, when we do an experiment in D2O, it becomes a good source of D plus and OD minus. Okay, so when I dissolve this compound in D2O, what I find and record the NMR spectrum. So D2O is a very good solvent to carry out these NMR experiments, because that's useful from the standpoint of minimizing the signal due to solvent. And so deuterium is NMR silent, so you don't see, if a proton is replaced by deuterium, you don't see a signal for it in the NMR spectrum. So what we find is that when you do this experiment, you see that gradually the signal that is corresponding to the carbon hydrogen bond actually disappears. Okay, so that is one of these hydrogen signals disappears, And then after you do the experiment, you take the molecule and measure the mass spec. The mass spec shows that there is a peak, which is M plus. Over here, it actually becomes M plus 1 plus. Okay. So this means that, the compound has picked up an additional, mass unit. And so now, based on these two data points, what we can propose is that one of these protons is actually going to be replaced by a deuterium. Okay. And so we'll look at the mechanism and all that shortly. But this is one of the conclusions that one could make from this experiment. And that is that, when I add a ketone to D2O, I do end up with a deuterated ketone as the product. Now, so if you think about it, what can happen is that you have this compound pH, C double bond O, and these are two hydrogens over here, CH3, CH3. And now, as we sort of looked at in the previous case, if there is small amount of D plus that is present in solution, so that's going to be floating around. And keep in mind that this is in D2O, and the bottles of D2O that we get are in 99.98% of D2O, really high amount of D2O. So it's unlikely that there's going to be even a small amount of H2O present. And so therefore this you can assume that it's almost 100% D2O in this reaction conditions. And so under these conditions, if it's lost, then you can think about this kind of a scenario wherein you produce pH, C, O. Just redraw this structure so that it's easier for you guys to look at it. So it's going to form O and then deuterium. And so this is a new double bond that is formed, and there is CH3 over here. And so you can imagine that this could be one of the components of the mixture. Okay. And now when this compound actually equilibrates, you can also think about the plus that is floating around in solution. And keep in mind that this forward process actually produces another mole of one equivalent of H plus. And because H plus is produced in such a small quantity, it's unlikely that the H plus will compete with D plus for the next step. So you will see here that, when this comes back, just surely by numbers, D plus is present in much larger quantity compared to H plus. And so you will end up with pH, C double bond O, and now instead of hydrogen, you have deuterium. Okay. And so the other hydrogen remains intact if you look at it. Okay. So this is how this compound gets converted to the deuterated version. And in NMR timescales and in the NMR experiment, we will not be able to observe the enol because the enol itself does not have a significant population for us to look at it. But you will observe that the compound on the left gets gradually deuterated to form the compound on the right, and the signal due to hydrogen is going to go down slowly, and it's going to produce this compound. Okay. Now another experiment that can be done as a follow-up is if you take this compound and this product, and I'm going to draw it separately in the next slide. So if I start with this compound, and now let's say I make this compound separately, and I start with this compound and I expose this to D2O. Okay. Now what we observe is that this signal due to this hydrogen gradually disappears, and you would end up producing the di-deuterated compound. Okay. And this is something that is very interesting. So you will get this compound. Okay. And so what it tells you is that, if there's enough time given, then this intermediary compound that is we see on NMR can actually get converted to the di-deuterated product. Interestingly, if I start with this compound or even with this compound, and I add in H2O instead of D2O, okay, and I allow the solution to sit for a while, and then I remove the water and I record the NMR spectrum, then I get back C double bond O, CH2, CH3. Okay, so what these series of experiments tell me is that enol is actually being produced, but on the NMR experiment we are unable to detect it. And second thing is that the production of the enol is a reversible process, and so once you form the enol can actually revert back. And further evidence for the reversibility is obtained when you take a deuterated compound, which is the product, what we think is the product, and add water to it, and we get back the starting material. So this is a very nice example of how you can actually demonstrate the principle of equilibrium, chemical equilibrium in the process. Okay, but together keep in mind that this is a reversible process, and we do detect this in the NMR as an intermediate, although we don't detect it in NMR, but we can infer its production by this NMR experiment. All right, so let's now discuss a little bit about catalyzing this reaction. So, enolization as a process can be catalyzed by acids and bases. So, as you saw in the previous lecture, the first step of the enolization actually involves picking up of a proton. So, similarly, we shall assume that that proton was generated in the medium, and so that can be one assumption. And usually in water, there's a very small amount of H plus and OH minus that's available. But you could also do accelerate the process by adding in a small amount of H plus. So imagine that we have this kind of let's say we add a drop of H plus, and so it's going to form hydronium ion. And as you know, hydronium ion's structure is like this, and it has a positive charge on the oxygen. So now this lone pair on this oxygen can pick up this proton and produce the corresponding protonated carbonyl. So it will be OH plus, and you have your three hydrogens in the alpha position, and this is the aldehyde. So you may notice that we have switched to an aldehyde in this example. But now there's clearly there's water that's present as the medium, and water can now come in here, and this carbonyl is activated enough that it can allow for this H plus to be picked up, and it's going to give you the product, which is the enol. So O, the H is already here, and then there's a double bond, and this is H, and these two hydrogens are going to remain intact. And so if we write them out, there are these two hydrogens here. And if you notice, the byproduct that is formed is H3O plus, which can then go back and catalyze the reaction. So if you want the enol to be produced, then all you need to do is to add a small amount of H plus in the reaction medium, and that can convert the keto to the enol form. Okay. Now we like this mechanism a little better because it actually shows that the water is attacking the keto form and producing the enol, rather than just spontaneous loss of H plus as we have discussed previously. Okay, now a similar thing can also happen with a base. So let me just quickly write that out. So you have an aldehyde O H H H and H, and now if you have OH minus, OH minus attacks here, and you can move this over here and produce the enolate directly. Okay, so you have O minus, there's a double bond here, there's a hydrogen here, and H. Okay, so this can be produced, and this is called the enolate, and we will come back to this later in the lecture. So it is called the enolate. And now again, this enolate can react with the hydrogen of water, so you will get O H H. If it picks up this hydrogen, then you're regenerating the base, and you're producing a enol. So this is the enol. Okay, and then you get hydroxide ion being kicked out, and this hydroxide ion can go back and react with another mole of aldehyde and form an enol. So the keto-enol tautomerism can actually be promoted significantly by adding a small amount of acid or a small amount of a base. Okay. Now with this background, now let's talk a little bit about the stability of this keto and enol forms. So as we discussed, if I draw out an energy profile, the keto form is a little bit more stable than the enol form. So this is the keto and this is the enol. And so there must be a small barrier that we need to overcome to get to from the keto to the enol form. Okay. Now, both the keto form and the enol form produce the enolate. That is, both the ketone gives you the enolate, and the enol also gives you the enolate. That is, if I have to draw it here, let me just draw it here. OH, the enol also gives you the enolate. Okay. So, but now since the keto and enol are going to give you the same intermediate, we can make some judgments about which compound is more acidic. Okay. Now let me just redraw this energy profile in the next slide so that we understand this better. So what I'm going to do is I'm just going to assume that the enolate is over here, O minus and H and CH2. Okay, and then we also have H plus that is going to be formed. And now let's assume that the keto form is more stable than the enolate. So the keto is here. And we already know that the enol is more unstable compared to the keto. So the enol is going to be here. So this is going to give you the enolate. This is also going to give you the enolate. And therefore, if you look at this structure over here, now we can assume that we can reliably deduce that the enol is more acidic. Okay, so between the keto and enol, because the enol is inherently more unstable, the reaction of the enol to give you the enolate is going to be more facile, and therefore the enol is going to be more acidic compared to the keto form. Okay, now let's compare the stability of the enolate with a few other known functional groups. So the first functional group that we want to compare it with is the alkoxide. So if I draw out the alkoxide, it's over here, H, H, and CH3, CH3H versus the corresponding enolate, which is double bond H, CH3, CH3. So if you notice, the difference between these two compounds is this CH2 over here, and this system is a conjugated system, and therefore the enolate is more delocalized compared to the alkoxide, and therefore one would expect that the enolate would be more acidic, or the enol would be more acidic compared to a regular alcohol. Okay, so with that, in the next lecture we will move on to understanding the molecular orbital picture of this system.